Look up on a clear night, away from city lights, and the Milky Way holds somewhere between 100 and 400 billion stars. Astronomers call this collection an ocean of stars, with currents running through it, storms tearing through calm regions, and new light seeding behind them. Take Proxima Centauri, 4 light-years away, a red dwarf so faint you need a telescope to see it. Now take Betelgeuse, 500 light-years off, marking the shoulder of Orion, so vast it would swallow every planet out past Jupiter. Almost nothing else matches between the two. Mass decides everything about a star's story: how hot it burns, how long it survives, and what kind of corpse it leaves behind. Astronomers sort stars by temperature and brightness on the Hertzsprung-Russell diagram, mapped in 1911. Most stars fall along a diagonal band called the main sequence, where hydrogen fusion in the core balances gravity for billions of years. Every star starts the same way, inside a cold pocket of gas and dust, light-years wide. Gravity slowly pulls the gas inward, clumping matter into a dense knot that begins to collapse under its own weight. Friction heats the collapsing core for thousands of years, while leftover gas flattens into a spinning disk around it. Jets of gas blast outward along its spin axis, slamming into surrounding gas and lighting it up for light years. After millions of years, the core finally reaches 10 million Kelvin, hot enough to fuse hydrogen into helium, and a star is born. In the Carina Nebula, James Webb's cameras found thousands of these young stars still wrapped in dusty cocoons. Most stars arrive in loose clusters, siblings born from the same cloud, drifting apart within tens of millions of years. Once fusion lights up, a star settles into a type. Astronomers sort them: O, B, A, F, G, K, M, hottest to coolest. Red dwarfs sit at the cool dim end, making up roughly 3 out of every 4 stars in the galaxy. Because they are small, red dwarfs fuse hydrogen slowly and gently, and convection stirs their entire interior. Estimates put a red dwarf's lifespan at 1 to 10 trillion years, far longer than the universe has existed. TRAPPIST-1, a red dwarf 40 light-years away, hosts 7 planets, 3 inside its habitable zone. Move up the mass scale, and you reach stars like our Sun, burning at 5,778 Kelvin, fusing 600 million tons of hydrogen every second. The Sun is about 4.6 billion years into a 10 billion-year run, already past the midpoint of its stable life. At the heavy end sit the O and B stars. Rigel, 860 light-years away, shines 120,000 times brighter than the Sun. Extra mass means extra gravity, so these stars burn hotter and faster, exhausting their fuel in just a few million years. Every main sequence star eventually runs low on core hydrogen. For a Sun-like star, that moment arrives after 10 billion years. The core contracts while a shell of hydrogen ignites around it, pushing the star's outer layers outward dramatically. A red giant is born, its surface cooling as it swells to tens of times its former width. Deep in its core, helium ignites in a runaway process called the helium flash, briefly outputting more power than an entire galaxy. The outer layers drift away into space in a slow, stellar wind, glowing as ultraviolet light from the exposed core ionizes the gas. This is a planetary nebula, like the Helix Nebula, 650 light-years away, expanding outward before fading within 10,000 years. Left behind is a white dwarf, Earth-sized, yet carrying half the Sun's mass, slowly cooling for over 1 trillion years. Massive stars swell too, but on a scale that dwarfs any red giant. Betelgeuse's radius is 764 times the Sun's. Even larger is VY Canis Majoris, nearly 1,400 times the Sun's radius, yet thinner than the air in a room. These red supergiants fuse helium, then carbon, neon, oxygen, and silicon in sequence, each stage faster than the last. Inside, fusion builds up layer by layer until an inert iron core sits at the center. Iron is the dead end of stellar fusion. When the iron core reaches 1.4 solar masses, gravity wins in under a second, and the core collapses from Earth-sized to 20 kilometers wide. The rebounding shockwave tears the rest of the star apart in a core collapse supernova, briefly outshining its entire host galaxy. SN 1987A showed this in 1987, its light arriving as a new visible star after 168,000 years crossing space. These explosions forge gold, platinum, and uranium, flinging them outward into the surrounding gas. What remains depends on mass. Between 1.4 and 3 solar masses, the collapsed core stabilizes as a neutron star, one of the densest objects known. A sugar cube of it would weigh 1 billion tons on Earth. The Crab pulsar, remnant of a supernova recorded in 1054, spins 30 times a second, sweeping beams of radiation like a lighthouse. Some neutron stars, called magnetars, carry magnetic fields 1,000 times stronger still, capable of starquakes that release enormous gamma-ray bursts. If the collapsing core exceeds 3 solar masses, nothing can stop it, and a black hole forms instead. Its gravity is so extreme that not even light can escape past a boundary called the event horizon. Cygnus X1, identified in 1964, pulls gas from a companion star into a blazing accretion disk reaching millions of degrees. Stellar black holes typically hold 5 to 20 solar masses, though some discovered in 2019 weighed as much as 70. Not every massive star waits quietly. Wolf-Rayet stars have already blown away their outer hydrogen through fierce winds, exposing their blazing hot cores. 635 WR102 holds the record for hottest known star, over 210,000 Kelvin, 36 times hotter than our Sun. 643. At the opposite extreme, red hypergiants like Stephenson 2-18 may reach 2,000 times the Sun's radius, so puffy their density rivals Earth's atmosphere. 653. Stars rarely live alone. More than half of all Sun-like stars belong to binary or multiple systems. 700. In close binaries, gravity can pull a stream of gas from one star directly onto its companion, sometimes triggering a sudden nova. 708. Star clusters take this further. The Pleiades hold a few thousand young blue stars born from the same collapsing cloud. 716. Globular clusters like Omega Centauri hold 10 million stars packed into a sphere just 150 light-years across, some over 12 billion years old. 725. Below the red dwarfs sits a population that never quite becomes a star. Brown dwarfs never gather enough mass to sustain hydrogen fusion. The coolest, like WISE 0855, sit colder than a kitchen freezer, likely forming icy clouds instead of steam. Some brown dwarfs drift entirely alone, rogue worlds unattached to any star, possibly numbering in the billions across the galaxy. Not every star burns at constant brightness. Cepheid variables swell and shrink on a clock tied directly to their true brightness. Henrietta Leavitt discovered this relationship in 1908, work that let astronomers measure distances across the universe with real precision. Edwin Hubble used exactly this method in 1923, proving Andromeda sat well beyond the Milky Way entirely. Stars also differ by when they were born. Population 1 stars like our Sun formed from gas already enriched with heavy elements. Population 3 stars, the very first generation, would have been enormous, forged from pure hydrogen and helium, and none has ever been directly observed. Mass alone does not set every record. R136A1 holds the mass title, roughly 196 times the Sun's mass, the most massive star confirmed anywhere. Close binaries complicate the tidy life story. Algol puzzled astronomers until they realized mass had been transferred between its 2 stars. When a white dwarf siphons hydrogen from a companion and approaches 1.4 solar masses, it triggers a runaway Type 1a supernova, leaving no remnant at all. Observations of these explosions in the 1990s revealed the universe's expansion was accelerating, a discovery that won the Nobel Prize in 2011. 2 neutron stars can also spiral into each other. In 2017, LIGO detected exactly this kind of merger for the first time. The collision produced a kilonova, forging an estimated 10,000 Earth masses of gold and platinum in a single violent flash. Near the Milky Way center sits Sagittarius A star, a supermassive black hole holding 4.3 million solar masses in a region smaller than Mercury's orbit. When a binary pair wanders too close, the black hole can fling one star away at speeds past 1,000 kilometers per second. A star's mass shapes any life nearby too. Around a red dwarf, the habitable zone sits close in, exposed to violent stellar flares. Around a sun-like star, the habitable zone sits much farther out, calm and stable for billions of years. Around a massive blue star, the zone sits far out too, but the star itself barely lasts a few million years. Nowhere near enough time for complex life. Line up the record holders and the range gets almost absurd. The smallest main sequence stars barely edge past Jupiter in diameter, while the largest, the red hypergiants, could swallow Saturn's orbit whole. The oldest stars still burning today formed within the universe's first billion years. HD 140283, the Methuselah star, may be over 13 billion years old. Every extreme on this list started from the same basic ingredients: hydrogen, helium, gravity, and time, arranged into wildly different outcomes. Zoom out and the whole galaxy has a lifespan too. Astronomers call the current chapter the Stelliferous Era, the age of active starlight. It began a few hundred million years after the Big Bang and will continue for roughly 1 to 100 trillion years. For now, molecular clouds keep collapsing into new stars, roughly 7 forming somewhere in the Milky Way every year, though that rate has slowed. Eventually, the raw material for new stars will run out. Red dwarfs, burning slowly and efficiently, will be the last stars standing. What follows is called the Degenerate Era, dominated by cooling white dwarfs, neutron stars, and black holes drifting for unimaginable spans of time. Long after that, black holes themselves will slowly evaporate through Hawking radiation, the largest taking a number so large astronomers call it a googol of years. What comes after, in a universe with no stars, no black holes, and no light, remains one of the genuinely open questions in modern cosmology. Step back outside on a clear night, and this entire range hides in plain sight. Sirius, 8.6 light-years away, is a main sequence star twice the Sun's mass. Canopus, 310 light-years off, is a rare, bright giant, shining 10,700 times more luminous than our Sun. Arcturus, an orange giant 37 light-years away, has already left the main sequence, swelling to 25 times the Sun's diameter. Vega, 25 light-years away, spins so fast its equator visibly bulges outward, completing a rotation in under 13 hours. Every one of these familiar points of light is its own case study in mass, age, temperature, and time remaining. The same sky that looks calm and unchanging from a backyard is, underneath, exactly as restless as the galaxy described at the start, full of nurseries, main sequence stars, giants, and quiet stellar corpses all at once. The Milky Way alone holds past 200 billion of these stories, and more than 1 trillion planets scattered among them. Every single one began the same way, inside a cold, collapsing cloud of gas, and every one will end differently, according to how much mass it carried at birth. Betelgeuse, still sitting in Orion's shoulder, will explode someday, possibly tomorrow, possibly in 100,000 years. Nobody can say precisely which. When it finally does, the resulting supernova may be visible on Earth in broad daylight, a spectacle not seen since a Chinese record from 1054. Our own sun keeps its slower, quieter appointment roughly 5 billion years out. A red giant phase, a fading planetary nebula, and a white dwarf ebbing for 1 trillion years. Somewhere in the gas and dust that outlives every one of these stars lie the raw materials, carbon, oxygen, iron, and gold among them, for whatever comes next. The ocean keeps moving, one star's ending quietly seeding another's beginning.